2. All right. So here we go. Yesterday, all right, we'll put it up. Yesterday, you guys, about not too many people were doing the lecture questions yesterday because I didn't give a lot of time. But then I had an email last night come in pretty late from a student said, hey, can you reset the lecture questions for me because I got kicked out or whatever and I didn't get a chance to do them. So I went in this morning to do that, and the first lecture questions were gone completely from the whole grade book. So I don't know what happened. My apologies on that. But if you don't mind going back and doing those, so go into week 9, or I also, when I put them back in there, I made them due tonight. So it should be on the right-hand side as well if you are in our if you're in our class. Okay. So I'll give you a second to redo those lecture questions. The other thing you do is you want to get out your packet. There is a little bit of a change here. Usually I make you do your notes on a piece of paper. However, these notes are quite challenging and they have graphs and they have tables and they have all these different things. So if you take a look inside your packet, and some students like to transfer this into their notebook, which I think is absolutely fine. I think that's great. So you have all of your notes together. But for the actual lecture portion today, I don't want it to be like super cumbersome of being like, why don't you draw that endothermic graph? So I gave you kind of a little guided notes. I don't love guided notes. But just for today, in the packet, there are some guided notes. And again, feel free to then transfer this information into your notebook so that you always have it available. Okay. Perfect. All right. Perfect. All right. So let's go ahead and get that started. I'll do some attendance a little bit later here. So today we're going to talk about a little bit of a harder concept. We're talking about endothermic, exothermic, and this idea of entropy. So you might be hearing some of these words in your other classes, but it's not something that I think that you have learned up until now. So yesterday was a very simple lecture. You're like, I know what a conductor is. I got it. Today is going to be a little bit different. This stuff can be a little bit confusing. So those of you at home, if you have any questions, please don't hesitate to stop me, because usually the day before this, we do a discovery lab where you're touching some things and looking at some reactions and doing stuff like that. We are modifying that lab, and we're going to try to do it on Thursday for you guys. And then at home, you guys will do it next Thursday. But we're going to get there. It's all about kind of thinking direction of energy flow, which can be hard. Okay. All right. So we got our lecture questions done. And today we're going to talk about endothermic, exothermic, and entropy. So you have these little notes, like I said, in your packet. If you would like to follow along, just kind of makes them go faster. The biggest issue when we're talking about endo and exothermic is the students have a very hard time differentiating the system from the surroundings. Okay, so let's define the system. The system, and that kind of starts at the top there, is the chemicals or the actual reaction itself. So it might not necessarily be the beaker, but it might be what's going on inside of it. Okay, so I have baking soda and vinegar up here. Boop, boop, boop. Put some baking soda in there. Hopefully everybody knows what happens when you mix baking soda and vinegar. We're going to get some bubs. Okay, no, don't boil over. All right, or not even boiling. But as you can see, the system would be the actual chemicals reacting inside of that beaker. The surroundings are everything else outside of that. Okay, everything outside of the system. I'm talking about the air around the chemicals. I'm talking the beaker around the chemicals. I'm talking the air around the beaker. If I were to put my hand on the outside of the beaker as well, everything outside of the system. Okay, if you were to do a reaction, and we'll do this on Thursday, with calcium chloride in water, okay, it ends up getting very warm. And so what you would see is that energy would leave the reaction and would go into your hand. Or the energy would, if you put this thermometer inside the beaker, okay, the energy would leave the reaction and go and hit the thermometer and heat the thermometer up, and the temperature would go up. So the thermometer would be in the surroundings and would be receiving energy or losing energy as well. Even if it's sitting inside that reaction, okay, the system is the reaction itself, and the surroundings is everything else outside of that individual reaction, okay? It seems simple until we start getting into it a little bit. Let's talk about exothermic processes first. So you see I kind of have a blank for it. Exothermic reaction or process. If you are going to exit a building, or if you have an exoskeleton, are you going inside or outside with exo?
Oh, outside.
Outside.
Is this like the exergonic and endergonic reactions?
You know, I'm not familiar with those terms. Are you have that in bio?
Yeah.
It might be the same thing. So what?
Because exergonic and endergonic like require energy and some like.
Sure. Yeah. Okay. Nice. So I see what that must be. This would be one that requires. So you were talking about requiring energy to start. This is going to talk about what it does with its energy throughout the duration of the reaction. So we're same process. You'll think of the same thing. I love it. That one probably the suffix means start. This one just means what it does with its energy during the reaction. Perfect. Hey, I love it. Look how these are cross-curricular now. Exo means out, and thermic means heat. Okay, so in an exothermic reaction, the system itself, the chemicals or the process itself, they are releasing energy. So you can remember just the terms, releases energy, and you can say in the form of heat if you want, whatever, but as long as you know it releases thermal energy. Okay, and what that's going to look like on the little side here is that when you have an exothermic reaction, you have more energy at the start. So I would say more here. And it releases energy. So this whole little hump here, we're going to talk about this soon. But when you're looking at whether or not it's endo or exothermic, you just want to look at how much energy you have at the beginning and how much energy you have at the end. And in an exothermic reaction, you have lost energy, and so you end up with less. So another way, if you would like to write that down in words, the reactants, remember these are the starting materials, have more energy than the products. And as the process or the reaction happens, it releases all of that energy. Okay. Awesome. So some examples of this would be I have a candle burning on my front table, correct? If I put my hand near it, what is it going to feel? It's going to feel warm. The energy is going from the reaction out to the surroundings. And it starts with more energy. And if I burn it, I can burn it all the way till there's no energy left, right? So it starts with more energy. So you would say a fire. You haven't done calcium chloride yet. We're going to do that on Thursday. The other thing that we have, I don't know if you've ever seen these. Have you ever seen these Hot Snaps hand warmers? Okay. They're liquid and there's a little crystal inside. Okay. And so you can just write fire as your example if you would like. What these little Hot Snaps do, they're actually quite cool. Usually I give one to every other person and let you pass them around, but you know, COVID. So what this is it's a nice kind of a liquid here, and there's what looks like a little coin inside. And I was told on my survey I should show more stuff here, which I'm trying to do. Okay, and what is sodium acetate? And what's going to happen is when it's in its liquid form, it has a lot of energy in it. And then what you do is you snap this little, this one's going to work. Beautiful. And as you can start to see, this little reaction is happening, okay? And it's turning from like a liquidy red into a solid. And what's happening with that, and the whole thing will turn that nice kind of color here. And when you feel this now, it is very, very warm. And the idea is that you take these little things with you when you go ice skating or skiing. And it was just a little snap of the thing. Now it's exothermic. So that means it's releasing heat energy as the reaction is happening, and it's making it hotter on its surroundings. Okay, so these are pretty cool. They're nice and warm. The nice things about these, which are, you're creating a solid, you're having a temperature change that usually would tell you it's a chemical change, but you can actually boil these and they will go back to their liquid state and then you can use them again. Okay, so, if you're looking for a stocking stuffer or whatever, hot snaps are pretty cool. You can get all different kinds. But that is very, very warm. So that means the reaction is releasing energy, or that is exothermic. Okay. All right. So let's talk about endothermic. If exo means out, endo means in heat. In heat. So your definition there is it absorbs energy from the surroundings as the reaction is processing. It absorbs energy from the surroundings. All right. Now, looking at our little graph over here, that means at the beginning you have less energy and you gain energy over time and you have more energy inside of your bonds. Now I'm talking about inside of the actual chemicals. Students will get very confused and say, oh, that means it must be hotter at the end. No. We're talking about how it's putting energy into its bonds and it's absorbing energy from the surroundings. Okay. So the products have more energy. Not that they're warmer, it's just that they have more energy. Okay. So your little example of that, have you guys ever seen these little cold packs? They have chemicals in them and they have a little bit of water. Usually what they have, and I don't know what this one has, is ammonium nitrate. I don't know if it's going to tell me what this one has. But what is going to happen? So you could say, we'll try baking soda and water. I might write, because you haven't done the lab yet, an ice pack. And what happens here, there's some little like Dippin' Dot feeling things in here and a little bit of water. When you mix the ammonium nitrate with water, when that reaction happens, it actually takes energy in from the surroundings. And what that would feel like to you, if you put your hand on this, oh my gosh, you don't have a thumb. Now you do, okay? You are the surroundings, and the system needs to take energy in. So the energy would go from your hand into the actual reaction itself, for lack of a better word, making it feel cold. So when it's endothermic, it would actually bring down the temperature because you're taking energy away from the thermometer. And when the thermometer feels a slowdown in molecular movement, okay, the temperature comes down. So endothermic, you're taking energy in and it's cooling down its surroundings, if that makes any sense. That's probably why it tends to be a little confusing. All right, let's get into entropy, shall we? Entropy. Entropy, in a shortened word, and I kind of put a little definition here. If you had to remember one word for entropy, it would be the word disorder. Entropy is disorder. So I always like to say, whose room at home is in a high state of entropy? Are you like a mess? You know where everything is, but it's not in its place. Or do you have a low state of entropy where you're like, and then this goes here, and then this goes here. Okay. So the major definition, or the regular definition, is the measure of randomness or disorder in a system. randomness or disorder of a system. Okay. And the more disordered, the greater the entropy. The more disordered, the greater the entropy. So you can just, say, no, my room's not messy. It just has a high state of entropy. That's fine. The more disordered, the greater the entropy. So if you kind of think about it like my little blocks here, okay, if you had a pile of blocks that were nicely set up, it would be a very low amount of disorder. And then if you have a pile of bricks and they're all over the place, this would have a very high amount of disorder. If your room is very messy, you're in a high state of entropy. So entropy is just disorder. Now, one of the laws of nature, kind of we've been talking about a lot of those here, is there's a general rule that nature favors more entropy. So that's why when you clean your room and a week later it's a hot mess again, is because nature tends to favor more entropy. If something can be pushed to be more disordered, nature will do that. Okay? Nature doesn't really like, it's hard to keep things structured and organized and things like that. Okay? Beautiful. So nature tends to favor more entropy. Awesome. We feeling good? Okay, now I kind of skipped some boxes, so we're going to go back and do those. Perfect. Let's fill in those little boxes, shall we? Because that was at the very bottom. So we're going to move from on your boxes here. We're going to talk about your low disorder to your high disorder. And we're going to give you the examples of each. You're going to want to kind of keep this in your head because this is how you're going to talk about if you're talking about if a reaction is spontaneous or not. You guys are honors, so I'm adding crystals in for you guys. It's not something I would do in my regulars, but the most ordered that something can get, let me see here. Okay, and this isn't even really, this is considered a solid, okay, where things stay in place and they move just about a little bit. A crystal, and I don't have a really good simulation of a crystal would be even more structured. I mean, I'm talking about everything has a shape and a pattern. So in the honors, we tell you that the lowest disorder, okay, are actually crystals. And if you could see it at a molecular level, okay, you would have an exact shape, an exact place. Everything has their exact, and they are very calculated things like diamonds, quartz, things like that. Then if we get a little more disordered, the next one is called a solid. Okay. You will know that it is a solid when you're looking at a chemical reaction because you'll see, and so I want you to write it down, this little S in a parenthesis. That tells you that whatever that chemical is in a solid state. Okay. So what you have here is you have a solid. The next thing that gets more disordered, and think about it's a mess or if it's moving around or if it's not organized, the next thing is a liquid. And the liquids are more unorganized because they can move past each other. Everything can kind of move around. So the next one is a liquid. You will note that it's a liquid by the little L next to it in a chemical reaction. And then the next one, you're like, oh, I know the next must be gas. And that's unfortunately not the way it's going to go here. The next one is actually when you have a solution. Okay. So what you see from an outside perspective, if we have some water, we're going to put some salt into the water. Okay. You just see it dissolve. If you could see another step into it, what you would see is that salt would actually break apart. Now we have not only our water swimming around, but we also have our salt particles swimming around. So if we can zoom in even further here, if I put some salt in there. Okay. So now not only is the water disordered, Now I have my sodium chloride swimming around in there all disordered as well. So the next step up is actually called an aqueous solution. And we talked about these in the last unit to kind of throw that out there when we talked about mixtures. It is one step more disordered than the actual liquid because you have put more stuff in it. Okay. And then the highest disorder that we have, obviously, go back to my simulator here. The most random, the most crazy, the most out of control any of your particles can get, and the most disordered would be a gas. And the way that you would write gas in a chemical equation is with a little g. Ooh. And then aqueous solutions has stuff inside of it, and then the gases are most disordered. So again, you might want to say, we're going to put our term in here. Crystals have low entropy, and gases have high entropy. Okay. If I could put a number to these things, and I'm talking like just this is a random number to try to talk to you about entropy. If I could say a crystal was a 1 on an entropy scale, and these numbers aren't real, I'm just trying to show you an order of magnitude, that a solid would be a disorder of 2. So it's not that much bigger. Okay. Then a liquid would have like a disorder of like a 5. And then an aqueous solution would have like a disorder of like 10. But then a gas would be like just multiple times larger in entropy. Gases are extremely disordered. Gases pretty much always win when you're talking about increasing or decreasing entropy. Okay? All right. So disorder, let's put it all together. Endo-exothermic entropy, and now we can talk about spontaneity. Are we ready? On to the back. So again, that's why my little entropy thing was funny, because it's ordered in the crystal side, and then it gets more disordered entropy, and nature does tend to favor more disorder. All right, spontaneity, here we go. When I have baking soda and vinegar up here, okay, we'll do it again. A little baking soda, little vinegar. Do I have to do anything to make this reaction happen, or just once they're together, they go, correct? That reaction of the lighting of the candle, I lit it, but once I lit the candle, is it just burning? Just burn, okay? These are 2 examples of what are called spontaneous reactions, a process that occurs without any ongoing outside intervention. That means you can start it, but you don't have to do anything to maintain it. Occurs without any outside intervention. Okay. So for instance, I have an ice cube right here. I'm going to put it right there. Is it going to melt? Yes. Am I actively doing anything to it to make it melt other than let it sit in the current environment? No, it's just melting. Okay. So 2 factors that will contribute to making things spontaneous. Here we go. It either has to be exothermic, which means it releases energy to its surrounding and heats up its surroundings, or it has to increase entropy. And there are going to be a whole bunch of, you can guarantee on your quiz, I'm going to say, here's a reaction. Is it spontaneous? Yes or no, and why? Now, the thing is that sometimes they work together and sometimes they don't. You have to have at least one. And if you have one of these 2 things, it can be spontaneous 99% of the time. Okay. All right. So let's go talk about my ice cube. My ice cube sitting right here, and this is not on your paper. We're just talking about this one. Your ice cube sitting right here. Am I doing anything to it actively to make it melt other than it's just in its environment? So this is a spontaneous reaction. But in order to be spontaneous, we need to figure out which of these two things is making it spontaneous. So the first thing is that my ice cube is not exothermic. In order to melt, my ice cube is taking in energy. So is that making it spontaneous? No. Perfect. That can't help me. But if you take a look here, what does my ice cube start at? It starts as a solid. And then at the end, my ice cube is going to be what? A liquid. Or maybe if you're like, hey, if it's made out of tap water, I know that that's not a liquid. Okay. But either way, we're making the ice cube. We're obeying the law of nature, saying that things want to be more disordered. That ice cube is moving this way. So that is why, okay, this is spontaneous. So the thermic nature of it is working against its spontaneity. However, the fact that it's increasing entropy is making it a spontaneous reaction. Okay, let's try another one because these are nice and challenging. So this is the hot pack that I just did. Okay, sodium acetate is NaC2H3O2. And I believe this is the one that is on your notes here. So why is the process the heat solution pack goes through? Is it spontaneous? So all I did was I snapped it and then the thing went on. Okay. So, whoopsies. Is it spontaneous? I thought that was going to be next. Yes, it is spontaneous. Woo. And we said that the temperature, okay, it was releasing energy. So if it's releasing energy and warming your outsides, it is exothermic. However, looking at our little slides here, the hot pack was an aqueous solution, and then it went to a solid. So what's happening to the entropy? Remember, this is low, and this is high. Is it becoming more disordered or less disordered? Less, so that's a problem. So what is driving the spontaneity of this? The reason that it just went, once I snapped it, it went by itself. What is making this spontaneous? The fact that it was exothermic, okay? You have to have one of the two. Sometimes you have both of the two, okay? But you have to have at least one of the two. Awesome. Let's try another example. I'm going to give you guys some time to do the practice worksheet and the post-lab questions. So this is the cold pack. You have ammonium nitrate, which is a solid, and then it goes into an aqueous solution. And the thing is, if I were to take the temperature of this and it feels cold, that means it's taking energy into the product itself. So if it's taking energy into the product to cool down its surroundings, that means it is endothermic. What's happening to the entropy if I'm going from a solid to an aqueous solution? Is it increasing or decreasing? The entropy is increasing. So thinking back to your factors here, we either have to be exothermic and or we have to increase entropy. So the reason why this one is spontaneous is because of its entropy. Very good. Okay. I'm going to let you do the last one by yourself, and then we'll go over it. So I'm going to give you about 30 seconds. I'm going to take some attendance on who is here at home. If I put liquid water in the freezer at 0 degrees Celsius, okay, you take your ice cube tray, you put it in the freezer. Do you have to do anything to it, or does it just freeze? It just freezes. So we know that it is spontaneous. Think about when you're cooling down an ice cube, which direction energy must be going. Are you putting energy into the ice cube, or is energy coming out of the ice cube? So tell me if it's endo or exothermic. And then think about your boxes and tell me if the entropy is increasing or decreasing. Okay. All right, let's take some attendance over here. Everybody else. All right, perfect. So The ice cube itself, this one was a toughie. Gave you a hard one at the end there. Okay. We have that it is actually becoming more ordered because it's going from a liquid to a solid. So that's not working well for our spontaneity. So that must not be it. However, you have your ice cube, and in order to slow down the particles to turn them into a solid, you actually have to remove energy. That's why you put it in a cold freezer, because it will be high. The energy of the freezer would be low. Everything goes from high to low, so the energy is removed from the ice or from the water, making it into an ice cube. So it's spontaneous because it is exothermic. Okay, so what I want you to do, we have about 8 minutes remaining. There is one more worksheet that I want you guys to do, and I want you to do your post-lab questions. And we are going to practice this more tomorrow. I realize that this is challenging, and you're like, I don't even know what she said. She just said, yeah, exothermic. I don't get it. So we're going to practice a little bit more. I want you to think about if it's endothermic, that means you start low, okay? Then there's a little hump, and you end high. Don't worry about this little hump. You just draw that in if you're drawing a graph. Exothermic, you start high, there's a little hump, and we'll talk about the hump later, and then you start low. So when you draw these graphs, really what I'm looking at is your reactants versus your products. In an endothermic, the products have more, and in an exothermic, the products have less. Okay. So however you want to draw that, and again, hump, boop. Wonderful. Okay. So what I want you to do is I want you to go in, do your 3 lecture questions. Hopefully it doesn't erase tonight. And then I want you to do this little half of a worksheet. Talk to me.
The lecture questions are...
No, there's always something. I appreciate your help with that. Let's see how I can make that work. Heavens to Betsy Lou. Submissions. Oh, disabled. That would make it so it wasn't. Oh, here we go. Enable until. Make that Thursday evening. And go. Okay, now it should be good. Thank you. Sorry. Okay, so this stuff is tough. Like I said, the lab that we're gonna do is going to pertain to this stuff. So hopefully we'll make it easier to understand after Thursday for you guys here, and after we have you guys back next Thursday at home. But so this is probably one of the tougher things in thermochem until we get into some of the math, but if you like math, it's not that bad. Okay, so I'm gonna put the music on quietly. I'm gonna walk around, see if you have any questions. Anybody at home have any questions before we get started here? Oh, there is a secondary little worksheet. It's called the Thermochemistry Endo Exo Entropy Recap. If you would work on that tonight, then tomorrow when we come in, we're gonna do thermochemistry worksheet number 2. Okay, so you guys working on that. I'm gonna wander around, see how you're doing. We got about 5 minutes. You hopefully can get your 3 lecture questions done in that amount of time. I know this is confusing. I know it's confusing. We're going to practice it more tomorrow. All right. Does anybody at home have any questions I can answer? I think I got everybody. I got everybody at home except for Corey. No Corey. Emily. No Emily. And Josh. Okay.